All right, my internet cut out again. I don't know what the problem is today. So, did you hear me when I got to the point where I found the particular solution 1/3 x cubed to the differential equation?
You froze when you were solving for C.
Oh, okay. So let me just repeat what I'm doing. I have this differential equation. Second order, constant coefficients. The right-hand side is a polynomial of degree 2. Because there's no y term there, I know I have to look for a solution of degree 3, a cubic. So I take a cubic, ax cubed plus bx squared plus cx plus d. I differentiate it once, I differentiate it twice. I take these two expressions and I put them into the differential equation. It means I add these two, and this is what I get. This quadratic polynomial, which has to equal x squared plus 2x. So the coefficient of x squared, 3a, has to equal 1. So a is 1/3. The constant term, this term, 2b plus 6a, that's the coefficient of x, equals 2. So if I divide by 2, b plus 3a is 1. 3a is 1. So b plus 1 is 1. b has to be 0. The constant term 2b plus c is equal to 0. b is 0, so c is 0. So I get that in this cubic, A, B, and C, A, B, C, and D. D can be anything. It's just, I'm not going to worry about that for the moment. But B and C are 0. A is 1/3. So in fact, a particular solution is 1/3 x cubed plus any constant. I'm just going to choose to make the constant equal to 0. How do you find the general solution? The general solution to a non-homogeneous equation is the general solution of the homogeneous equation plus a particular solution to the non-homogeneous equation. This is a particular solution to the non-homogeneous equation. For the general equation, again, I can think of this as y double prime plus ay prime plus by equals 0. A is equal to 1, b is equal to 0. The discriminant d, which is a squared minus 4b, is equal to 1. K, which is 1/2, the square root of d is 1/2 of 1 is 1/2. So we get for the general solution of the homogeneous equation, y is equal to e to the minus a over 2x. A is 1. So e to the minus 1/2 x times c1 e to the kx, x over 2, plus c2 e to the minus kx, x over 2. So this is the general solution for the homogeneous equation. And for the original problem, it's this plus my y1. So y is equal to c1, minus x over 2 plus x over 2 is 0, plus c2, minus x over 2 minus x over 2 is minus x, plus 1/3 x cubed. So that is the winner. That is the solution to the equation.
So my
All right, speak a little louder, please.
yes, for degree number 2 polynomials, I need to use a cubic form always.
No, it depends on the differential equation. If you had a y term here, you would look at it for a quadratic. If you have no y but a y prime, you look for a cubic. If you have no y or y prime, just y double prime, you would look for a polynomial of degree 4. It depends on the differential equation, what kind of polynomial you look for. Okay. Other problems from these earlier homeworks that I should go over? I'm happy to spend as much time as you need on this.
Page 350, problem number 4.
Okay.
Thank you.
So which page? What page number?
Page 350, exercise number 4.
Okay. Page 350, number 4. So this is in the section on homogeneous equations. And we have y prime equals x squared plus 2y squared over xy. So this function on the right-hand side, f of xy, is equal to this. And let's just check. If you multiply x and y both by t, so you look at f of tx comma ty, that's tx squared plus 2 ty squared over tx times ty. Okay. If you compute f of tx comma ty, this is what you get. In the denominator, I have t times t, which is t squared xy. In the numerator, I have t squared x squared plus 2 t squared y squared. I can factor a t squared out of the numerator. I get that. And I see that I have a t squared here and a t squared here. They cancel. So this is just equal to x squared plus 2y squared over xy, which is f of xy. So this says that this equals this. This means that this function f is homogeneous. And the technique that the book is giving in this section for solving a homogeneous equation is to let y equal x times v. So we introduce a new function v defined to be y over x. And in that case, y prime, which is the derivative of x, 1 times v, plus x times the derivative of v, is going to be equal to what? That's equal to x squared plus 2 y squared, xv squared, over xy, which is x times xv. So I substituted that in. And you'll notice, so this is v plus x v prime equals, I have x squared plus 2x squared v squared over x squared v. I can factor x squared out of the numerator, and I get some cancellation. These cancel. So this is 1 plus 2v squared over v. Or 1 over v plus 2v. Any questions about that so far? I have a v in it. Yeah, go ahead.
Yes, at the first look, that exercise, how do you know if you're homogeneous without doing the process?
I know it's homogeneous because I checked. You need to check. Otherwise, you don't know.
Thanks.
So let me subtract the v. I get xv prime is 1 over v plus v. Or v prime equals, let's see, this is actually 1 plus v squared over v times 1 over x. And now this equation is separable. So I started with this homogeneous equation. I used a technique for dealing with homogeneous equations, and it gave me a separable equation. Another way to write this is that v over 1 plus v squared dv dx equals 1 over x. So I can integrate with respect to x, or integrate, I get this. And I know how to integrate this. I need to multiply and divide by 2. And then on this side, I have 1/2 the log of 1 plus v squared equals log x plus c. So let me multiply by 2. The log of 1 plus v squared is 2 log x plus c, which is log of x squared plus c. V is y over x. So this is the log of 1 plus y squared over x squared, which is the same as the log of x squared plus y squared over x squared. This equals the log of x squared plus c. So the log of x squared plus y squared, this is the log of x squared plus y squared minus the log of x squared, equals 2 times the log of x squared, or the log of x to the 4th plus c. And when I exponentiate, I get x squared plus y squared equals some constant times x to the 4th. So that's the solution. Pretty good. So you really do need to be able to do calculus to solve these problems. You need to know all the techniques from calculus 1, actually. Right now, we don't need anything from calc 3 or intermediate calculus. and whatever techniques you have from high school algebra. All of that is necessary. Any other problems? Any other questions about this? Other questions I should do? Look at it for a minute and let me just jot down attendance and then we'll continue. Let's see. I have someone named Jay, but I don't know who Jay is. You just tell me your last name so I can. Yeah, Lee. Oh, Jeremiah Lee. Okay. Gotcha. All right. If there are no more questions about this problem, let me talk a little bit about the application problems for second order equations, and really just the first one, which is the one you see most often in physics and engineering, which are simple harmonic oscillator. So this is section 8.18. Basically, simple physics problems that have to do with simple harmonic motion. And I had assigned some problems at the end of this section. Which I'm going to go over. I think I had assigned problems 1 to 7. So if you've taken a little bit of physics or even probably learned this in calculus, if you have a particle which is moving in a straight line, let's say from 0, and it moves towards 0 from wherever it is, and the acceleration of the particle is proportional to how far away the particle is from 0. So if you're out here, let's say this is some position y, you're going to be pulled into 0. You're going to accelerate towards 0. So if y is positive, the acceleration, if it's going to the left, is negative. On the other hand, if y is negative to the left of 0, then you're going to accelerate towards 0, and the acceleration will be positive. So the sign of the acceleration is opposite to the position, the sign of the position. If y is positive, this is negative. If y is negative, this is positive. And there's some constant, which is positive. I'll call it, I can write it k squared if it's positive. So every positive number is a square. So the differential equation for simple harmonic motion is y double prime is minus k squared y, or we could write it as y double prime plus k squared y equals 0. Now, we know what the solutions of this equation are. The basic solutions are sine of kx and cosine of kx. And if you take y to be any linear combination of these, this is the general solution. So the general solution of the differential equation for simple harmonic motion is, if it's y double prime plus k squared y equals 0, it's sine kx cosine kx. Now there's a very nice way to combine these two. So it really involves only one trig function, either the sine or the cosine, whichever you prefer. And I'm going to rewrite this so we get y is just some, only involving the cosine. And so there's sort of a trivial case. If a equal b equals 0, then y is just 0 for all x. So it means that if your particle is sitting at 0, it never moves. It's just there. So the real case is when a, b are not both 0. So one or the other or both of these numbers is non-zero, which means a squared plus b squared is positive, right? Because whenever you square a non-zero number, you get something positive. And I'm going to define a squared plus b squared as c squared. So let c be the positive square root of a squared plus b squared. So c squared equals a squared plus b squared. Now, another way of saying this is that if you take a over c and square it, and b over c and square it, you get 1, right? Divide this equation by c squared, this is what you get. Now, if two numbers squared add up to 1, then they lie on the unit circle. This is the circle, x squared plus y squared equals 1. A over c and b over c are some point on the circle. And let's call this angle alpha. So this is the angle with one leg on the positive x-axis and the other going to the point a over c, b over c on the circle. Okay. So look at that picture for a minute. It's, it's very simple, it's baby, geometry or trig or something, but whether it's just the Pythagorean theorem. But a over c comma b over c, it satisfies the equation of the circle, ax squared plus y squared equals 1. So it lies on the circle. And it makes some angle alpha with the positive x-axis. I mean, alpha, if you wanted to write it down in some sense, the tangent of alpha is this over this. So this is the arctangent of b over c over a over c, which is the same as the arctangent, because the c's cancel, of b over a. So that's this angle alpha. This is the unit circle. The cosine of alpha is a over c, and the sine of alpha is b over c. Any questions about this?
The polar coordinate is applied also. The the polar expression.
I'm sorry, I don't
Okay.
understand what you're asking.
Oh, okay.
I mean, this is, I'm not looking at polar coordinates. I'm just looking at the rectangular coordinates of this point on the circle. So for this angle alpha, the cosine is A over C and the sine is B over C. So if I plug this into the general solution that I already have, that's the solution of the equation. But I can write A as C cosine alpha and B as C sine alpha. So Y is equal to C cosine alpha, that's what A is, sine kx, and B is C sine alpha cosine kx. And I know the addition formula for the sine, Y is equal to C. This is exactly the sine of the angle kx plus alpha. So I can combine the sine and the cosine, and I get this perhaps simpler way to express my simple harmonic motion. For this function, this is periodic. When x is 0, this has the value C sine alpha, and then it oscillates. And the maximum value is C and the minimum value is minus C. So C is called the amplitude of this oscillation. It's oscillating between plus C and minus C forever. The frequency, the period, how long it takes for this to repeat, is 2 pi over k, and the frequency is defined to be 1 over the period, which is k over 2 pi. So these are just the words that are used in describing a simple harmonic oscillator. So if the acceleration of your particle is proportional to the displacement y, in this way, y double prime is minus k squared y. Y is the displacement. It's how far your particle is displaced from this point 0, which is the center of the oscillation. It oscillates according to this way, up and back forever. Any questions about this? This is just solving one of the simplest second order equations. Now, sometimes you have some damping. You have some force which is, I think, opposite to the motion. Well, it's actually not necessarily opposite, but you have some force which is proportional to the velocity, right? So for this function, we have y is the displacement or the position. Y prime is always the velocity of the particle. Y double prime is the acceleration. And sometimes we have what is called a damped vibration. For example, if you think of a pendulum swinging back and forth in a vacuum with no force on it other than gravity, it would swing forever. But you have air resistance, which is proportional to the velocity, and it's slowing it down. So in a damped vibration, you have an external force proportional to the velocity. So we started with the differential equation, y double prime plus k squared y equals 0. And if there is a damping on this, an external force proportional to the velocity, it'll be something plus there'll be some constant times the velocity y prime. And we might want to write the c times the velocity, but it's just more convenient. Makes the algebra simpler a little bit. If I just write the constant multiplying the velocity in the form 2 times c. And so the damping means that the c is not equal to 0. It can be positive, it can be negative, but not 0. Otherwise, it's just simple harmonic motion. And k is always positive. So let's go back. Here's my equation, y double prime plus 2c y prime plus k squared y equals 0. This is second order linear ordinary differential equation. Constant coefficients and homogeneous. So in the notation we're used to using, my a is equal to 2c and my b is equal to k squared. So the discriminant d is equal to a squared minus 4b. That's 2c squared minus 4 times k squared. That's 4 c squared minus k squared. Right? That's the discriminant. And I want to look at the behavior of this oscillator in 3 cases: when the discriminant is 0, when it's positive, and when it's negative. So if d is equal to 0, the general solution is y equals e to the minus a over 2x. So a over 2 is c minus cx times a plus bx. What happens to this? So if c is positive, this is a linear over an exponential. This goes to 0 as x goes to infinity. So if you wanted to think of this as some oscillating pendulum, it's oscillating, but the oscillation is getting smaller and smaller and smaller, and in the limit it approaches 0. So this is called critical damping. If you look at y as a function of x, when x is 0, this is 1a, this is a. Now, if a plus bx is always positive, this is just going to decay. And if at some point a plus bx equals 0, then this is going to come down, but then it's also going to have to go back up again. So this is the picture of your oscillatory motion in the case of when the discriminant is 0 and C is positive. If C is negative, or less than or equal to 0, in fact, sorry, C can't be 0 because we're looking at the damping case. If C is less than 0, then this is e to a positive exponent, y goes to infinity. So every solution goes to infinity, plus or minus, depending on whether this is positive or negative. But this solution blows up. Okay? So that's how your oscillator looks in the case when the discriminant is 0. Suppose D is positive. Which means C squared is greater than K squared. So what does our equation look like in this case? So again, we have y double prime plus 4cy prime plus k squared y equals 0. The general solution is y equals e, whoops, this is a 2, e to the minus cx. And let's see, so the d is 4c squared minus k squared. So let's call it h, is 1/2 the square root of d, which is 1/2 square root of 4c squared minus k squared. Take the 4 out, you get 2, which cancels that. So so h is equal to the square root of c squared minus k squared. And you get a constant a e to the hx plus b e to the minus hx. This, in the case when d is positive, is the general solution, which I can write as a e to the h minus cx. I'm just multiplying through by minus c e to the minus cx plus b e to the minus h plus cx. And h squared equals c squared minus k squared. So h squared minus c squared is minus k squared, which is negative. This factors h minus c, h plus c is negative. So one of these is positive and one of these is negative. So if h minus c is positive, h plus c is negative. Sorry, if h minus c is positive, h plus c is negative. So minus h plus c is positive, and y goes to infinity. If h minus c is negative, then h plus c is positive. So this is negative, minus this is negative, and y goes to 0. So we have, this is what's called overcritical damping. And in the third case, d is 4, c squared minus k squared is less than 0. So c squared is less than k squared. And in the case when the discriminant is negative, your general solution is y equals e to the minus cx times some linear combination, a of sine hx plus b cosine hx, which we saw we can combine into just one sine function, sine of hx plus alpha. Okay. Okay. Well, I mean, the interesting thing is what happens when we try to solve some problems. So let me spend a few minutes working problems. On page 339. Exercise 1. So in all these exercises, y is a particle moving in a simple harmonic motion according to the equation y equals c sine of kx plus alpha. Right? So in 1 through 5, we're in the case where we have the sinusoidal motion. Okay. So this is a simple harmonic oscillator. There's no damping. So in problem number 1, we're told that, so we have to find the amplitude C if y equals 2 and y prime equals 4 at x equals 0. All right, well, y of 0 is c times the sine of k times 0 plus alpha. That's c sine of alpha. That's equal to 2. If y is equal to this, y prime, when you differentiate, you get kc cosine of kx plus alpha. So y prime of 0 is kc times the cosine of alpha, and that's equal to 4. Oh, and we're also told that the frequency is equal to 1 over pi. The formula for the frequency is k over 2 pi. So this means that k is equal to 2. So we have our two equations, c sine alpha equals 2 c cosine alpha equals 4. So c cosine alpha also equals 2. So the sine of alpha and the cosine of alpha are both equal to 2 over c, which means alpha is, let's say, pi over 4. Of because the only angle when cosine is either pi over 4 or 5 pi over 4. Let's say pi over 4. And in that case, c times the sine of pi over 4, sine of pi over 4 is root 2, equals 2. So c is equal to 2 root 2. That's the amplitude. That's what we had to find. Any questions about this? No? Okay. Let's look at problem 2. So again, we have y is equal to c sine of kx plus alpha. And we're told for this simple harmonic motion, the amplitude is 7. The frequency is 10. Amplitude is 7, frequency is 10. Find velocity when y is 0. Okay. Well, amplitude equals 7 means c equals 7. The frequency, 2 pi over k, 2 pi over k is the period. So the frequency k over 2 pi is equal to 10, which means k is equal to 20 pi. So y is equal to 7 times the sine of 20 pi x plus alpha. When is y equal to 0? So when y is sitting right at the origin, when y is equal to 0, the sine of 20 pi x plus alpha is 0, which means 20 pi x plus alpha is some multiple of pi. What is the velocity? It's y prime. Y, when you differentiate it, you get kc cosine kx plus alpha. C is 7, k is 20. 20 pi times 7 times the cosine of 20. So this is kc cosine, what is k? 20 pi. 20 pi x plus alpha. 20 pi x plus alpha is n pi. What is the cosine of n pi? Plus or minus 1. Minus 1 to the n, 140 pi. So as our particle is moving back and forth, when it's approaching from the right, the velocity is 140 pi. When it's approaching from the left, the velocity is plus 140 pi. That's the answer. Any questions about this? Okay, let me just do one more. Maybe number 4. So number 4 is, so we have y again is c sine of kx plus alpha. So this is the equation of motion. Find the equation of motion given that y equals 3 and y prime equals 0 when x is 0, and the period is equal to a half. So let's recall the period is 2 pi over k, and if that's equal to a half, that means that k is 4 pi. So y is equal to c sine of 4 pi x plus alpha, and y prime is 4 pi c cosine of 4 pi x plus alpha when I differentiate. So when I let x equal 0, y at 0 is c times the sine of alpha, and that's equal to 3. And y prime at 0 is 4 pi c cosine of alpha, and that's equal to 0. So cosine alpha equals 0, which means alpha is pi over 2 plus some multiple of pi, perhaps, plus any multiple of pi. So what is y? Sorry, I can also get c. So what is c? C is 3 over sine alpha. That's 3 over the sine of, what is alpha? Pi over 2 plus n pi. So this is plus or minus 1. Let's just say I take n 0 or n even. This is 3, and it's minus 3 if n is odd. So y is equal to 3. Let me be very, so this is the same as minus 1 to the n times 3. So y is minus 1 to the n times 3 times the sine of 4 pi x plus alpha pi over 2 plus n pi. Then we expand this using the addition formula for the sine. This is minus 1 to the n 3 times the sine of 4 pi x cosine pi over 2 plus n pi plus the cosine of 4 pi x times the sine of pi over 2 plus n pi. Now, this is really pretty because sine of, The cosine of pi over 2 plus n pi, that's 0. And the sine of pi over 2 plus n pi is minus 1 to the n. So this term cancels, and what I get is minus 1 to the n times 3 times minus 1 to the n times the cosine of 4 pi x, and minus 1 times minus 1 is plus sign. I get 3 cosine of 4 pi x. That's the answer. So for number 4, if we have this simple harmonic motion with displacement 3 and velocity 0 when x is 0 and the period's a half, this is exactly the equation of motion of our particle. That's kind of nice. Are any questions about any of these problems? There are a couple more that I'll do on Wednesday, and I'll answer questions on Wednesday. Remember, our first exam is a week from Wednesday. So Wednesday is basically just going to be for review and answering questions. Next Monday, there's no school. CUNY is closed for, I think, Columbus Day. So Wednesday is review, and a week from Wednesday is the midterm. Any questions about anything? Yes, no? Okay. If not, then we are done for today. Be back on Wednesday.
Thank you. Take care, Professor.
Okay.
Take care, Professor. See you Wednesday.
The midterm is everything on ordinary differential equations. We spent the first week talking a little bit about PDE from the other book, but that's not going to be on the midterm. The midterm is just this ordinary differential equations.
Okay.
Okay, bye all.